Welcome to the debate. Right now, artificial intelligence is, well, it's fundamentally shifting global healthcare from a reactive model, where we essentially wait for a disease to strike and then just scramble to manage it, to a highly predictive model. We are talking about intercepting pathology before it even begins. As we face these massive global health crises, particularly things like obesity and diabetes, a critical divergence has emerged in how we should deploy these incredibly powerful computational tools. The central question we are examining today is this: as we face global health crises, should the primary focus of AI-driven medical innovation be on mapping and modulating the human microbiome, or on predicting and reversing insulin resistance through real-time multimodal data? I will argue that the microbiome, our so-called forgotten organ, is the foundational root of human health, and that AI's unprecedented ability to process complex metagenomic data is the ultimate key to global precision medicine.
And I will argue that insulin resistance is the more immediate actionable threat to global health, and that leveraging AI to analyze existing proxy data like standard consumer wearables and continuous glucose monitors offers a far more scalable and pragmatic solution to averting our current metabolic epidemics.
To truly understand the stakes here, we have to grasp the sheer scale of the human microbiota. We aren't just talking about a little bit of digestive bacteria. We are looking at vast, highly complex communities of microorganisms across the intestines, the skin, the mouth, the respiratory tracts. It's roughly 39 trillion microorganisms.
Right.
They literally outnumber our human cells 10 to 1. It is practically an alien civilization living inside of us. And this forgotten organ actively regulates our immunity, our digestion, our metabolism, our mood, and, even how our bodies respond to vaccines.
The biological elegance of that system is absolutely undeniable. But we also have to look at the immediate crisis burning down the house right now.
Exactly, and that crisis is often driven by dysbiosis, which is a fundamental microbial imbalance. If we look at the 2026 World Health Organization data, the numbers are, well, they're staggering because they are all deeply interlinked. We have 1.9 billion cases of obesity. We have 537 million cases of diabetes. We're seeing 1.9 million deaths a year from colorectal cancer and 280 million people suffering from depression. Historically, studying this ecosystem was prohibitively expensive and incredibly slow. Next-generation sequencing generates just massive amounts of data. We're talking 100 gigabytes of big data per single sample just from 16 srRNA, which identifies the bacterial genome, or shotgun sequencing, which reads the full genomes. Human minds simply cannot process that.
Which is exactly where the bottleneck always was. You couldn't act on the data because you couldn't even read it efficiently.
Precisely. Before unsupervised machine learning, processing 100 gigabytes per sample was like trying to read every book in the Library of Congress using a magnifying glass. But today, AI enters the equation. We use unsupervised clustering techniques, specifically algorithms like k-means and dbScan, to process petabytes of this data instantly. To put it simply, imagine walking into a party of 39 trillion people and having an AI instantly find the 5 distinct friend groups. It groups these vast microbial communities into distinct enterotypes. For the first time, we actually have the computational power to map, predict, and ultimately correct human health at its foundational ecosystem level.
I hear that, and I completely acknowledge the deep physiological importance of the microbiome. But we must pivot our focus to the immediate mechanical crisis at hand. Insulin resistance is the silent saboteur underlying our global health collapse. It is driving a catastrophic crisis of 540 million type 2 diabetes cases globally by 2025, and projections suggest those numbers could easily double by mid-century. We have to look at the physiological breakdown happening right this second in hundreds of millions of people. The cells in the muscles, the fat, the liver, they simply stop responding properly to insulin. The key doesn't turn in the lock anymore.
And because the key doesn't turn, the glucose just lingers in the bloodstream.
Exactly. And that lingering glucose acts like shards of glass in the vascular system. It triggers a massive cascade of systemic inflammation and fat buildup, leading directly to heart disease, polycystic ovary syndrome, and non-alcoholic fatty liver disease. Now, the real tragedy here is that traditional diagnostic tests fail us completely. Take the standard HbA1c test. It's like looking in the rearview mirror. It averages your blood sugar over 3 months, meaning it only catches the disease after the biological damage is well underway. And the so-called gold standard test for insulin resistance, the hyperinsulinemic euglycemic clamp, is totally impractical.
For the listeners who might be rusty on their endocrinology, remind us why the clamp is such a logistical nightmare.
Oh, it is a grueling process. You are literally strapped to an IV in a clinical lab for hours. Doctors are simultaneously pumping you full of insulin and glucose to artificially stabilize your blood sugar, just to measure exactly how resistant your cells are. It's invasive, it requires a dedicated clinical team, and it is entirely unscalable for a global population. This is where AI completely changes the paradigm. We don't need to sequence petabytes of novel biological matter. AI replaces those expensive, invasive clinical clamps by analyzing real-world proxy signals that we are already collecting. We are fusing data from continuous glucose monitors, wearables, electronic health records, imaging, genomics. By applying superhuman pattern recognition to these inputs, AI is achieving correlation coefficients of up to 0.95 with that gold standard clamp. We can stop disease progression precisely when and where it happens.
But relying on that data assumes everyone is constantly connected to these monitoring devices, doesn't it?
I come at it from a different way when we talk about what is truly scalable. The data required to predict and intervene in insulin resistance is already being generated by billions of people globally right now. Think about the infrastructure we already have actively in place. Right now, 10 million people worldwide are walking around wearing continuous glucose monitors, or CGMs, like the Dexcom or the Abbott Libre, tracking their interstitial glucose minute by minute.
But a CGM is still a dedicated medical device. Not everyone has one or can afford one.
Beyond CGMs, standard everyday consumer wearables are tracking activity, sleep, and crucially, heart rate variability. A consistently low HRV is a direct autonomic nervous system signal of the underlying systemic inflammation linked to insulin resistance. The AI can flag the risk just from how your heart beats while you sleep. We don't even need advanced wearables. We can use simple standard electronic health record data. If an algorithmic model sees triglycerides over 150 milligrams per deciliter and HDL cholesterol under 40, combined with a simple waist-to-height ratio, it flags the metabolic risk instantly. We are even seeing unconventional, highly accessible inputs like voice analysis being used. AI can analyze the microtremors in human speech to measure stress levels, because cortisol is a hormone that directly drives insulin resistance. The scalability of insulin resistance AI isn't some future theoretical framework. It is actively running on the hardware sitting in people's pockets today.
I see why you think that, but let me give you a different perspective on scalability. You are framing microbiome analysis as this cumbersome, lab-bound process, but the logistical hurdles of microbiome AI are being overcome at a pace that is frankly astonishing. It is scaling much faster than anyone anticipated. We are not just talking about wealthy tech hubs where everyone has a smartwatch. Look at Africa, where zipline drones are actively delivering offline AI sequencing kits to remote clinics. You drop a physical sample in a tube, the drone flies it to a centralized sequencing hub, and the AI processes it.
But is that data actually representative? Because historically, genetic data has been overwhelmingly skewed towards certain populations.
That is exactly why the Global Microbiome Conservancy is actively training diverse AI models across 100 different countries to ensure true global representation. And the sheer volume of data processing is reaching unprecedented heights. Let's look at China. The CAS Microbiome Initiative recently sequenced 100,000 urban samples. Now, 100,000 might sound small compared to millions of smartwatches, but the AI used deep learning to link urban pollution in those samples to a specific loss of microbial alpha diversity. That single computational discovery fundamentally maps the metabolic health risks of 1 billion Asians. So while a smartwatch provides a great localized proxy signal for a single patient's glucose spike, microbiome AI is mapping the environmental and biological realities of entire populations at a scale that fundamentally alters massive public health strategies.
That is a fascinating environmental insight. But let's talk about what that mapping actually achieves for the patient sitting in a clinic today versus active immediate intervention. When we look at predictive power versus root cause intervention,
The AI architectures dedicated to insulin resistance don't just predict disease at a population level, they actively reverse it in the individual. We are seeing deep neural networks, specifically long short-term memory networks, or LSTMs, that devour continuous CGM time series data.
LSTMs are traditionally used for things like language processing, right? Because they remember sequence and context.
Exactly. And that is why they are perfect for glucose tracking. They don't just look at a glucose spike in isolation. They recognize the temporal sequence, the melody of your blood sugar over days and weeks. A 2024 Mayo Clinic study across the US, Europe, and Asia showed that these LSTMs can predict the Matsuda index, which is the absolute clinical holy grail proxy for insulin sensitivity, with 88% accuracy using just 14 days of wearable data. That is staggering clinical accuracy extracted from a consumer device, and it translates directly to reversal. In the US, Vertahouse AI is analyzing CGM data from 20,000 patients and actively reversing insulin resistance in 60% of them through personalized, highly targeted ketogenic coaching. In Europe, the PREDICT-IN study spanned 10 countries, using basic EHRs from 1 million patients to deploy hospital AI that flagged prediabetes 2 full years earlier than traditional methods. That slashed disease progression by 25%. We are not just mapping an ecosystem. We are computationally nudging human behavior in real time to reverse a fatal trajectory.
The nuance there is that behavioral nudges, telling someone to eat fewer carbs or take a walk based on a glucose spike, that simply manages the symptoms. Microbiome interventions fundamentally repair the broken biology. When we utilize graph neural networks, or GNNs, we aren't just looking at a flat list of bacteria.
How did GNNs differ from the clustering you mentioned earlier?
If unsupervised clustering is like identifying the distinct friend groups at a party, graph neural networks are mapping the complex social dynamics of the entire city. They represent bacteria as nodes and the metabolites they produce as the edges connecting them. For instance, AI revealed precisely how one specific bacteria, Bifidobacterium infantis, literally feeds Akkermansia muciniaphila, which is a vital anti-inflammatory microbe. We are identifying the exact mechanistic levers of human health. In France, the MetaHit project applied these GNNs to 1,200 European metagenomes and was able to predict dysbiosis in 90% of cases. And it goes far beyond prediction to profound clinical success. Look at Italy, where AI-guided fecal microbiota transplants for C. difficile infections are achieving a 94% success rate. By processing these metagenomic graphs, we are moving past behavioral symptom management.
We are literally repopulating and repairing the damaged ecosystem that caused the metabolic dysfunction in the first place. That is true structural root cause intervention.
I'm sorry, but I just don't buy that. Let me tell you why I think the root cause argument misses the reality of immediate, widespread, diverse application. You mentioned drones flying samples to centralized hubs, but the reality is that metagenomic sequencing is still highly complex and resource-intensive. Meanwhile, insulin resistance AI is already fundamentally democratized for the most resource-constrained areas on Earth right now. Look at India's Beat-O app. It actively serves 5 million users today.
And how are they gathering metabolic data without CGMs in those areas?
By using the hardware already in their hands. The app fuses the user's basic smartphone camera with simple blood selfies. The AI analyzes the camera input, using it to detect skin tone as a highly accurate proxy for jaundice and liver function. Its LSTM model literally outperforms standard WHO diagnostic criteria in urban slums where traditional medical labs don't even exist. In Brazil, the Fiocruz institution deployed federated learning across their public health system hospitals. They pulled 50 million patient records to successfully predict PCOS-related insulin resistance. Because it was federated learning, the AI trained on the data locally at each hospital without ever centralizing the private records. In Kenya, Apollo Agriculture is doing something incredible. They're linking satellite crop data with farmer vitals to map food insecurity directly to metabolic resistance risk, allowing organizations to distribute aid effectively before the metabolic collapse happens. These applications are incredibly diverse, They are globally scalable, and they require nothing more than the basic digital infrastructure that already exists right now.
If we're discussing broad clinical applications and diverse applicability, the microbiome's reach is astonishingly broad across the globe. And it goes far beyond just metabolic metrics. Because the microbiome is the foundational bedrock of the immune and nervous systems, AI analysis of it is solving wildly disparate medical mysteries that wearables simply can't touch. Consider the gut-brain axis. An Israeli study with 1,000 patients used AI to link low levels of lactobacillus in the gut directly to the motor progression of Parkinson's disease.
That is remarkable. Predicting neurological decline from gut bacteria?
Exactly. In oncology, AI detected Fusobacterium nucleatum in 85% of Canadian colorectal tumors, paving the way for targeted bacterial interventions against cancer. We are even seeing AI save lives in neonatology. In 2025, AI saved a Kenyan baby from necrotizing enterocolitis by analyzing and optimizing the maternal microbiome before the condition could destroy the infant's intestines. And regarding your point on diverse global adaptation, microbiome AI is proving to be the true universal tool because it natively adapts to local realities. In Saudi Arabia, the Gut AI platform specifically adapts its machine learning models for halal diets, reducing obesity by 25%. In Brazil, Biome 4 Life crosses microbiome data with the staple diets of rice and beans, personalizing metabolic health for 200 million people based on what they actually consume. It doesn't rely on Western commercial wearables tracking step counts. It relies on the universal biological language of the microbes we all carry, contextualized by the specific foods we actually eat.
That is definitely a powerful framework.
That's an interesting point, though. I would frame it differently when we look at how these fields are beginning to converge. The fact is, the microbiome directly influences insulin resistance. They are not entirely separate, competing phenomena. The data clearly shows that low levels of Akkermansia specifically act as a primary biological signal for insulin resistance. The dysbiosis I am talking about is often the direct biological precursor to the physiological breakdown you're tracking with your continuous glucose monitors.
That's a compelling argument. But have you considered that this exact overlap proves that multiomics is the undeniable future of all this? We aren't going to have to choose between a microbiome model and a wearable model. The immediate trajectory of the technology is entirely about multimodal fusion. Apple's 2026 smartwatch update already promises live edge AI resistance alerts processed directly on the wrist, meaning it doesn't even need to ping a cloud server to warn you of a metabolic spike. Inevitably, that edge AI will be fused with proteomics and the very microbiome data you were talking about. We are looking at global consortia like the International AI Diabetes Alliance, which has a stated goal of developing universal multi-omics apps by 2030. Furthermore, we are seeing the dawn of quantum AI.
How does quantum computing change the timeline on this?
It drastically accelerates the hyperparameter tuning required to build what we call personalized plants in silico. Instead of strapping you to an IV in a lab, we build a flawless digital twin of your entire metabolic and microbial state inside the computer. The future isn't just knowing your enterotype from a gut sample. It's fusing the enterotype with a real-time CGM feed, your sleep data, and your genetics, and adjusting your metabolic profile minute by minute.
I agree that convergence is inevitable, but I maintain that the ultimate endgame of this convergence will still be realized through the microbiome. Once we map these massive multi-omics models, the medical intervention won't be a push notification on your watch telling you to skip a meal. The ultimate solution, projected by 2035, will be pharmacos vivos, engineered live probiotics. We will use AI-edited CRISPR to directly correct the dysbiosis in the gut. The precision of the wearable data you advocate for will ultimately be used to deploy the biological interventions I am describing. We will literally program the internal ecosystem to inherently resist metabolic failure, completely bypassing the need for constant, exhausting behavioral modification.
It is certainly a bold vision for where the biology is heading.
As we draw this discussion to a close, I want to summarize the position I've brought to the table today. The human microbiota, with its 39 trillion microorganisms, is the undisputed foundation of our physical and mental health. By unleashing artificial intelligence to map this staggering complexity, using unsupervised clustering to map enterotypes and graph neural networks to model biological interactions, we hold the ultimate map to predictive health. The clinical and economic implications are profound. According to McKinsey, this approach is on track to save $1 trillion by 2030, in part by cutting 40% of intestinal surgeries and aggressively preventing the onset of the global epidemics we face. Correcting the biological ecosystem at its root is the most permanent path forward.
And to summarize my stance, while the biological ecosystem is undeniably vital, intercepting the silent saboteur of insulin resistance remains the most practical, immediate, and scalable way to avert our metabolic crisis right now. By utilizing highly accurate multimodal data fusion from CGMs, standard wearables, EHRs, and even basic smartphone cameras, AI is uncovering subtle disease patterns that traditional clinical tests completely miss. This approach reaches from modern urban centers to remote clinics globally without the need for complex laboratory infrastructure. The clinical impact is happening today. As recent meta-analyses show, AI detection combined with targeted lifestyle nudges can avert 40% of preventable diabetes cases right now. We are stopping the progression of the disease exactly where it manifests in the real world.
It is clear that while we debate the primary focus, both fields are not only vital but are increasingly intertwined. The use of federated learning, which you brought up earlier, is a perfect example of this convergence. Both microbiome research and insulin resistance tracking require massive global data sets to train their algorithms. Federated learning allows us to train these incredibly complex models locally across thousands of hospitals without ever centralizing the underlying data. This fundamentally protects patient privacy while still aggressively advancing the science.
Absolutely. And we both share a profound reliance on explainable AI, particularly tools like LIME, which stands for Local Interpretable Model Agnostic Explanations. This is crucial for building trust with clinicians. A doctor won't just blindly follow a black box algorithm. LIME highlights exactly why the AI flagged a patient's insulin resistance or dysbiosis, breaking down the specific variables that led to the prediction. The multiomics future will demand nothing less than complete transparency.
The complex, deeply interconnected web of human biology guarantees that there is so much more to explore in this material. The systems we've discussed today, from engineered probiotics and AI-edited CRISPR to personalized digital twins and quantum metabolic mapping, represent just the beginning of how computation will finally decode our biology.
Indeed. We leave it to you, the listener, to weigh the evidence and decide which AI frontier holds the most immediate and profound promise for securing our global metabolic future.
Thank you for joining us for this rigorous exchange of ideas. Have a great day.